Hello, everyone. So last time we looked at the concept of relations and different types of relations. So we defined a relation R on a set A as a subset of A cross A. So you know that A cross A means the set of all pairs where the first and second coordinate comes from a set A. Now, if I have a subset of A cross A, then that is called a relation on A. And then we define the different types of relations. For example, reflexive relation. Reflexive relation means a relation where every element of the form A and A is in R, for every A in A. Then we define symmetric relation. Symmetric relation means A and B in R implies B and A is in R. So for example, if 1 and 2 is in R, then 2 and 1 must be in R. Or if 1 and 3 is in R, 3 and 1 it must be in R. In a symmetric relation. Antisymmetric relation means a relation where if A and B is in R and A and B are different elements, then B and A is not allowed to be in R anymore. So for example, if 1 and 2 is in R, well, 1 is not equal to 2, so 2 and 1 is not allowed to be in R. Or if 5 and 3 is in R, for example, then 3 and 5 is not allowed to be in R because, again, 5 and 3 are different elements. Okay, so this is an antisymmetric relation. If A and B is in R and A and B are different elements, then B and A is not allowed to be in R anymore. Transitive relation. Transitive relation means if element A and B is in R and B and C is in R, then A and C must be in R. Okay, so whenever A and B and C is in R, A and C is in R in a transitive relation. So in a transitive relation, if 1 and 2 is in R and 2 and 3 is in R, then 1 and 3 must be in R. And so on. And composition of two relations. So composition of two relations is defined similar to the definition of composition of two functions. So A and B is in SOR. When can I say A and B is in SOR? If R and S are relations. If there is some element C where A and C is in R and C and B is in S. So see, SOR in the concept of composition of functions as well. You saw that, composition of functions means like you connect two functions as in two machines. Each function acts like a machine, right? So we have a relation R that goes from, so if I call this set, for example, A, and this set B, and this set C, so then I have a relation R which goes from A to B, and a relation S that goes from B to C. Now, if I want to go from A to C, the relation would be SOR. SOR means first you have to find the action of R and then action of S. So when can I say that some element of the form A and B is in SOR? If there is some middle element C, if I can find the middle element C where A and C is in R and C and B is in S, then I can say that A and B is in SOR. Okay, so for example, when can I say 1 and 3 is in SOR? If there's, for example, if there is some element C, for example, let's say 2. If 1 and 2 is in R and 2 and 3 is in S, then I can say 1 and 3 is in SOR. Okay, so this is a composition of two relations, and then we define R2 as ROR. Okay, R2 is defined as ROR, R3 is defined as ROR2, which is same as R2OR, and similarly R4 as R3OR or ROR3, and so on. Now, the theorem that we wanted to prove last time was saying that a relation R on a set A is transitive if and only if R to power n is a subset of R for every n equals 1, 2, 3, and so on. So to prove this, we first said, so suppose that R to power n is a subset of R for every n equals 1, 2, 3, and so on. And we said that this means that R to power 2 is a subset of R, right? Because this is true for every n, 1, 2, 3, and so on. So R to power 2 is a subset of R. And so what does that mean? R to power 2 is a subset of R. What do we want to show? We want to show that the relation R is transitive, right? And what do we know? We know that R to power 2 is a subset of R. So we have to look at the definition of transitive. What was it saying? When can I say that the relation is transitive? If whenever A and B is in R and B and C is in R, then A and C is in R. So I assume A and B is in R and B and C is in R. So by definition, what can I say? I can say that A and C is in ROR, right? Do you remember the picture I draw for you for the composition? See, if A and B is here, and B and C here, but here both of the sets are R, and all the set both the relations are R, and all the sets are, let's say, some set A. So A and B is in R, B and C is in R. Then I can say that A and C is in ROR. So what does that mean? A and C is in ROR. It means that A and C is in R2. But I am assuming that R2 is a subset of R. R2 is a subset of R. So if A and C is in R2 and R2 is a subset of R, well, that implies that A and C is in R, right? This is the meaning of a set subset of another. If set number 1 is a subset of set number 2, that means each element in set number 1 must be also in set number 2. So here A and C is in R2 and R2 is a subset of R, therefore A and C is in R. Well, that's it. So this shows that the relation is transitive. So we showed that if A and B is in R and B and C is in R, then A and C is in R. So that means R is transitive. Okay. Now the other part of the theorem, next. Suppose that R is transitive. And we want to show R to power n is a subset of R for every n equals 1, 2, 3, and so on. So the best way to prove this is by using induction. We will prove this by induction. So if n equals 1, R to power 1 is R, which is obviously a subset of R itself. So suppose that, so this is the base step, which is okay. Now suppose that R to power K is a subset of R. So inductive step. And we want to show that R to power K plus 1 is a subset of R as well. So R to power K plus 1 is a subset of R. How can we show this? So R to power K plus 1, R to power K plus 1 is equal to R O R K, right? So I want to show that this is a subset of R. So let me take some element. So let A and B, and this is same as R, K O R, by the way. Let A and B be in R to power K plus 1. Then what can I say? Then there exists C, right? Such that A and C is in R, and C and B is in RK, right? This is again, remember the definition of composition of two relations. When can I say that some element A and B is in R or RK? So this is R, this is RK. So A, and this one, this one, call it C, and this one B. When can I say that A and B is in my relation? If A and C is in R, and C and B is in RK, right? If A and C is in R and C and B is in RK, then I can say A and B is in composition RKOR. Okay. So here I'm using the fact that RK plus 1 basically is same as RK OR. Okay. Now, A and C is in R, C and B is in RK, but my assumption was that RK is a subset of R, right? So since RK is a subset of R, we can conclude that C and B is in R as well, right? See, C and B here is in RK, and RK is a subset of R by assumption inductive step. So I can say that C and B is in R. Again, the meaning of subset, right? If RK is a subset of R, means every element in RK must be in R as well. So C and B must be in R. Now, A and C is in R, and C and B is in R as well. And I'm assuming that R is transitive. Remember, here in this part of theorem, we're assuming, suppose that R is transitive. We're assuming that R is transitive. So A and C is in R, C and B is in R, R is transitive. That means A and B is in R. If R is transitive and A and C and B are in R, then that means A and B must be in R. And we wanted to show that, remember, I took A and B in R to power K plus 1, and I showed that A and B is in R. So we showed for any element or any pair A and B in R to power K plus 1, we have A and B is in R. So that means R to power K plus 1 is a subset of R. If every element in R to the power k plus 1 is in R, well, that means R to the power k plus 1 is a subset of R. All right. So this was the proof of theorem. Now let's look at so then we want to do the next section we want to do is 9.4. So we'll skip 9.2 and 3. And then we do, and also 9.4, we skip 9.4 as well. We do 9.5 equivalence relations. So those sections are related mostly to graph theory, matrices. So those courses, or some algorithmic stuff as well. So for example, matrices, graph theory, graph theory will see in 225 matrices, you see 252. And in a more advanced course, you can see the connection between relations and matrices, or relations and graphs. Okay, but for this level, we want to do equivalence relation, which is an important topic and related to what we're doing right now. So 9.5 equivalence relations. Okay, so let's look at the definition of an equivalence relation first. So definition, I think I mentioned last time, definition of equivalence relation, but let's look at it again. So a relation R on a set A is called an equivalence relation if R has three properties: reflexive, symmetric, and transitive. So if R has these three properties, reflexive, symmetric, and transitive, then we say that that relation is equivalence relation. Okay, and the notation that we use is notation if for an equivalence relation R, we have A, R, B, we write A is equivalent with B. So this notation is same as A, R, B, or that is same as saying that A and B is in R. But it's just a notation that, so this notation, the first notation, is used for any relation. But if the relation is an equivalence relation, then we can also use this notation. Okay. And another definition for an equivalence relation R, define the equivalence class A, equivalence class, as follows. So equivalence class of R, we define it as set of all elements, let's say B in R, such that A and B is in R. And this is same as let's say B in A. Remember, all the elements come from a fixed set A, right? So equivalence class of A, where A is in R, A is in A, is defined as all elements B in A, where A and B is in R. Or same as saying that all elements B in A, where the element B and A is in R. So this is called equivalence class of A. Okay, so let's begin some examples. Example, let A equal, let's say, Z. Define the relation R on A as follows. So A or B if absolute value A equals absolute value B. Okay, so now you want to show that R is an equivalence relation and find the class of, for example, 2 and class of -1. So R, to show R is equivalence relation, we need to show 3 things. R is reflexive, symmetric, and transitive. So first part, solution. First part, to show R is equivalence, is an equivalence relation. So first we have to show that, so R is reflexive. Why is R reflexive? So we have to show that for every A in A, and our A here is Z, can we say that A and A is in R? When can I say that A and A is in R according to the definition of the relation? I can say that if absolute value A is equal to absolute value A. Well, that's obviously true, right? So for every A in Z, absolute value A equals absolute value A. So that means A and A is in R. Second property I have to check, R is symmetric. Symmetric means for every A and B in Z, if A and B is in R, then I can conclude that absolute value A is equal to absolute value B. Well, this obviously implies that absolute value B equals absolute value A, and then that means B and A is in R. Symmetric means if A and B is in R, then B and A must be in R. So absolute value A and B is in R means absolute value A equals absolute value B, but that itself means absolute value B equals absolute value A. Therefore, B and A is in R. And third property, transitive. For every A and B and C in Z, if A and B is in R and B and C is in R, then we can say that absolute value A equals absolute value B and absolute value B equals absolute value C. So one pair being in R means that the absolute value of first element is same as absolute value of second element, and absolute value B equals absolute value C. So these two together imply that absolute value A equals absolute value C, and that means A and C is in R. If absolute value A equals absolute value C, that means A and C are in relations, or A and C is in R. That's it. So we showed that if A and B is in R and B and C in R, then A and C in R. So that means the relation is transitive. So second part of, so that means R is equivalence relation. R is an equivalence relation and then the second part we want to see whether we want to find the equivalence classes of 2 and -1. So equivalence class of 2 means all the elements B in Z such that absolute value 2 is equal to absolute value B. So that means all elements B in Z such that B is equal to ±2, right? So equivalence class of an element means all the elements in the original set which are in the relation with the given elements. So which elements are in relation with 2? All elements whose absolute value are equal to absolute value of this element, which is absolute value 2, which is 2 itself. Now, absolute value B equals 2. It's a very simple equation. Absolute value B equals 2 means that B is equal to either 2 or -2. Well, all elements B and Z where B is equal to 2 or -2. Well, this just means a set with 2 elements, 2 and -2. Okay, so this was the second part. And then and also the equivalence class of -1 is can be found similarly. Equivalence class of -1 is the set of all elements B and Z such that absolute value -1 is equal to absolute value B. And this means, all B and Z such that absolute value B is equal to 1. And this means all B and Z such that B is equal to plus or -1. So this is a set with 2 elements, -1 and 1. Okay, so class of 2 is the set 2 and -2. Class of -1, equivalence class of -1 is a set -1 and 1. Okay, so let's look at another example. Let A equals the set of all real numbers this time, and define the relation R as follows. So X, R, Y, if absolute value X minus Y is less than 1. So in this type of relation, in this relation, 2 elements are in relation with each other, or X, R, Y, if absolute value X minus Y is less than 1. Okay, this is how we define this relation. Now, is this relation an equivalence relation? So again, we have to answer a few questions. Equivalence relation means reflexive, symmetric, and transitive. So let's check them. So for reflexive, we can say that for every X in R, absolute value X minus X is 0, which is less than 1. And that means X is in relation with X itself. So for every X in R, X is in relation with X itself. For symmetric, for every X and Y in R, if X and Y is in R in the relation, then what can I say? Then we can say that absolute value X minus Y is less than 1. And then that implies that absolute value y minus x is less than 1 as well, right? Because absolute value x minus y is same as or equal to absolute value y minus x. And therefore, absolute value y minus x less than 1 means that y and x is also in the relation. But we show that if x and y is in the relation, then y and x in the relation. So that means our relation is symmetric. So transitive means what? Means if x and y in R and y and z is in R, can I conclude that x and z is in R? But let's see. In other words, if absolute value x minus y is less than 1 and absolute value y minus z less than 1, can I conclude that absolute value x minus z less than 1? So what do you think? We have three numbers, x, y, z. Absolute value x minus y less than 1, absolute value y minus z less than 1. Can I conclude absolute value x minus z less than 1? The answer is no. So for example, let's say x equals 1.1 and y equals, let's say 2, z equals 2.9. So this is the counter example. See, absolute value x minus y is how much? 0.9, which is less than 1. And absolute value y minus z is also 0.9, which is less than 1. But absolute value x minus z is 1.8, which is bigger than 1. So x and y is in R and y and z is in R. But x and z is not in R. So that means R is not transitive. R is not transitive means R is not an equivalence relation. Okay. So if R is not an equivalence relation, then of course we cannot define or we cannot find equivalence classes either. So in order to find equivalence classes, first your relation needs to be an equivalence relation, but it's not an equivalence relation in this case. All right, next example. Let A again equals a set of all real numbers and define the relation R as follows. So A R B if A minus B is an integer. So show that R is an equivalence relation. And find the class of, for example, equivalence class of 1.1. So the first part, again, we want to show R is equivalence relation. Like previous examples, we have to show three things: reflexive and symmetric and transitive. So first part, reflexive. So we have to say that A for every A in R, and for every A in the set of real numbers, what can we say? We can say that A minus A, because when can I say that two elements are in relation? If the difference between them is an integer. So if I have A and A here, A minus A is 0, which is an integer. So that means A and A is in R. And second part, so second property, basically, second property about symmetric. Symmetric for every A and B in R. If A are B, then A minus B is an integer. So this implies that B minus A is an integer. And this implies B are A. Right, so if A are B, then A minus B is an integer. And if A minus B is integer, B minus A is also integer. Why? Because B minus A is the minus of A minus B, right? So if, for example, X is an integer, minus X is also integer, right? So B minus A is integer, but B minus A integer means B is in relation with A. So we showed that if A and B is in R, then B and A is in R, so which means the relation is symmetric. And finally, for reflexive, for transitive, if A and B is in R and B and C is in R, then what can we conclude? So then we can say that A minus B is an integer and B minus C is an integer. Thus, we can conclude that A minus B plus B minus C is an integer, because, sum of two integers is an integer. Sum of two integers is an integer. So if A minus B and B minus C is an integer, then A minus C is an integer as well. And that means A and C is in R. Okay, I think the screen was freezed for a few moments. So let me explain one more time. For reflexive, we want to show that the relation is equivalent. So we have to show reflexive, symmetric, and transitive. For reflexive, A minus A is always 0 for every A. So A and A is in R. Symmetric, if A and B are in relation, that means A minus B is an integer, which implies B minus A is an integer. Therefore, B is in relation with A as well. And for transitive, if A and B is in R and B and C is in R, then A minus B is an integer and B minus C is an integer. So the sum of these two, which will be A minus C, will be also an integer. And A minus C being integer means A and C is in R. So we showed if A and B and C are in R, then A and C is in R. So which means the relation is transitive and also symmetric and reflexive. So that means R is an equivalence relation. So second part of the question, I want to find a class of 1.1. So class of 1.1 means the set of all elements X in R such that X is in relation with 1.1, which means all elements X in R such that X minus 1.1 is an integer. So which elements minus 1.1 as an integer? Well, it's going to be 0.1 itself, or 1.1 itself, right? Let's say 1.1, because 1.1 minus 1.1 is 0, is an integer. What else? 2.1, right? 2.1 minus 1.1 is 1, that's also integer. 3.1 minus 1.1 is 2, is also integer. 4.1 and so on. And also from the other way, so we could add integers, positive integers to 1.1 or negative integers to 1.1, still minus 1.1, those will be integer. For example, so let me say union 0.1, right? 0.1 minus 1.1 is minus 1, which is an integer. Or let's say minus, so if I add minus 1 to this, right? If I add minus 1 to this, I'll get this. If I add minus 2 to this, I'll get minus 0.9. Minus 0.9 minus 1.1, that's also an integer. Or I can add another minus 1 to this, so minus 1.9, minus 2.9. So I could write this one as 1.1 plus k, where k is in n, union 1.1 minus k. Minus k, where k is in n, and also 1.1 itself. So I could add some positive integer to this, or subtract some positive integer to this from this, and in all such cases, that result minus 1.1 will be integer. So I could denote this with this notation, or I can also write this union of these two sets in this form: 1.1 plus a positive integer minus a positive integer, or 1.1 itself. All right, now another example, congruence mod M. So this is a very important type of equivalence relation. So again, let A equal Z and assume that M is a positive integer. Define R as follows. So A, R, B, if M divides A minus B, i.e. if A is congruent B mod M. So show that R is an equivalence relation and find class of 2 and class of 1 for M equals 2. So R is equivalence relation is easy to prove. So again, first part, R is reflexive. Why is it reflexive? We have to show that. So for every A in Z, A minus A, which A minus A is 0, and M divides 0. So that means A is in relation with A itself, right? Because if M divides A minus B, then we can say that A and B are in relation. And second part, symmetric. For every A and B in Z, if A are B, and if A are B, then we can say that M divides A minus B, and then this implies that M divides B minus A as well. Right? ARB means, according to the definition, M divides A minus B. But M divides A minus B implies M divides B minus A as well. Is this obvious? Because, if M divides A minus B, I can say A minus B is equal to, let's say, MK for some K. And therefore, this means B minus A is equal to M times minus K, right? And therefore, M divides B minus A. And M divides B minus A means B R A. And finally, transitive. Transitive if A are B and B are C, right? Then what can we say? Then we can say that M divides A minus B and M divides B minus C. ARB means what? Means M divides A minus B. BRC means M divides B minus C. So these two, because see, if A minus B is equal to MK, B minus C is equal to, let's say, MK prime. Then we can say that A minus C, the addition of these two will be MK plus MK prime, which is M times K plus K prime. So I can conclude that M divides A minus C as well. If M divides A minus B and M divides B minus C, then M divides A minus C according to this reasoning. A minus B equals MK, B minus C equals MK prime. This, if I add these two equations, I get A minus C equals M times K plus K prime. Therefore, M will divide A minus C. And this means that A are C. M divides A minus C, according to the definition of the relation, means M means A are C, because A are B if M divides A minus B. A are B and B are C. This implies that A are C. So our relation is transitive. So we showed that. So R is an equivalence relation. And for M equals 2, we wanted to find the equivalence classes. For M equals 2, equivalence class of 1. We want to find equivalence class of 1 and 2. See the other part? Equivalence class of 1 means what? Means all the elements B in Z such that B is in relation with 1. When can I say that two elements are in relation in this type of relation, which is congruence mod M and M is 2? So that means all B in Z all B in Z such that B is congruent 1 mod 2. So which elements are congruent 1 mod 2? So the remainder of them when divided by 2 must be 1. So that means odd numbers, right? Which elements have the feature that when divided by 2, their remainder are 1? Well, exactly odd numbers. Odd number means a number when you, such that when you divide it by 2, the remainder is 1. So this means all elements of the form 2k, so it's all a set of all odd integers, or means 1, 3, 5, minus 1, minus 3. Similarly, equivalence class of 2, B in Z such that B R2, which means all B in Z such that B congruent 2 mod 2. And this is same as saying that B congruent 0 mod 2, right? Because 2 itself is congruent 0 mod 2. Remainder of 2 when divided by 2 is 0. So B congruent 2 is same as saying that B congruent 0 mod 2. So which elements have the property that when we divided by 2, their remainder are 0? So just the even numbers, right? So this means the set of all even numbers. And that means 0 to 4, minus 2, minus 4. All even numbers. When divided by 2, their remainders are 0. Okay, so we showed congruent, the equivalence class of 1 instead of all odd integers. Equivalence class of 2 is the set of all even integers. So note, in example above, observe that there is no intersection between equivalence class of 1 and equivalence class of 2, and the union of equivalence class of 1 and equivalence class of 2 is the set of all integers, which was my A. Okay, so here I have two sets with no intersection, right? One of them odd integers, one of them even integers, and their union, the set of union of odd integers and even integers is set of all integers. So this is a property that always equivalence classes have. So any two of them will have are either equal or they have empty intersection, and the union of all equivalence classes will be your whole set. Okay, so first I wanted you to observe this fact for this specific example, and then we will prove this in general as a theorem.